And the credit valuation adjustment is the following. It is the adjustment I do to the valuation of derivatives to account for the possibility that my counterparty defaults while he owes me money. Okay, do you remember, when we talked about derivatives, you remember that we saw the following. We said each derivative contract carries a potential credit exposure with it. And remember that we had the IRS, and we had the PFE of the IRS, potential future exposure, was proportional to notional times the standard deviation of interest rates times the square root of t that elapses times the square root, the time that remains. And you remember we had something like this, and for this is the large tenor, and this is roughly, you remember that from the previous lecture. Kilonewton, exactly. You remember that. Now it comes as no surprise, since there is credit exposure, there is a credit risk. Okay? And this credit risk needs to be mitigated. It first of all needs to be measured. It needs to be priced. Okay? In exactly the same way that when I extend a loan, I say, I give you 100. The risk rate is 2%, but you also have, say, a 5% probability of default with zero recovery. So I will not charge you 2%, I'll charge you 7%. Okay? To cover for your probability of default. In exactly the same way, when I enter into a derivative transaction, which is over the counter and is not margin, I have to take into account the probability of default of the other guy, okay? And I'll have to price the other guy appropriately to account for the probability of default. Okay? Now, this is very roughly, this is the only thing you need to know about CVA. Okay? Now, the easiest way to visualize this is the following. Okay? Suppose that I don't measure the PFE, but I measure another. You remember PFE is the 99th percentile upside of the mark-to-market. Suppose I'm not interested in the 99th percentile upside of the mark-to-market, but I'm interested in something much more modest, and it's the average exposure of the mark-to-market. Now, the 99th percentile and the average exposure of, say, an interest rate swap or of any other kind of transaction, they have pretty much the same profile. It's just that the average exposure is like this. Let's say this is average. And the PFE is much higher. Okay, because the PFE is the 99th percentile of distribution. This is the average exposure. Suppose I found that average exposure. We'll look into it in a while. Suppose I found this average exposure. Okay? And suppose I have 10 years. This is here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? I have 10 years. I want to measure, okay, the probability adjusted amount of loss, okay, that's embedded in this transaction for the entire period of 10 years. Okay? How would I go about doing this? I can have a loss which may occur the first year, the second year, the third year, the 10th year, or not at all. Okay? Suppose I tell you that, say, in the first year, the average exposure, you know what the average exposure is. The average exposure is, say, 1 million. And the PD is 1%. Okay. Remember, the average exposure is kind of a, probability adjusted average of the mark-to-market. We'll go into it in a little more detail. PD is 1%. Just intuitively speaking, the fact that this PD is 1% and it's not 0, and say recovery is 0, okay? Just intuitively speaking, this 1% probability of default, how much credit risk does it create for the first year? Suppose this was not an average exposure, this was an actual exposure. I said, in 1 year, I expect to get from you back 1 million, but you have a probability of default of 1% and a recovery of 0. What would be really my cost of risk? We had this tree before, it was very intuitive then. Say I have a 99% chance of getting 1 million, a 1% chance of getting nothing. So the risk neutral expected value of this prospect that I have is how much? 190K. Okay? Forget the risk-free discounting here. It's 190K. I would have had 1 million if this was owed to me by God. It would be worth 1 million. Now it's worth 990K. What's the difference? 10K. What's this 10K? 10K is this. It's 1% times 1 million. Very intuitive. Just a binary tree. So, if the average exposure of the first year is 1 million, the cost of risk of the first year is PD times average exposure of the first year. Let's go to the second year. If the average exposure of the second year is, say, 1.3 million, and the PD in the second year, suppose I tell you that it is 2.5%, then what would be the contribution of the second year's exposure to the total risk? It would be 1.5 million times 2.5%. And so on and so forth. If I knew the probabilities of default for all the years, okay, I'll get to it how I could get those probabilities of default, but if I had known them, and if I knew the average exposures for all the years, what would be my total reduction in value due to credit risk of this counterparty? It would be the sum over all the years, average exposure for the year I, times PD for the year I. Okay? And now let's make this a little more realistic. Of course, if there's a default event, I will not lose everything. There is always going to be a recovery rate. So I have to reduce this by the recovery rate. And of course, something else, both in my risk-free case and in my risky case, when I try to find the net present value today, I have to discount with a risk-free discount factor. Okay? Risk-free discount factor. This is it. This is my CVA in this very simple case. By the way, what is a very big simplification I made here? It's so big and so intuitive that you didn't even notice me making it. I said, expected exposure multiplied by PD. Expected exposure, what is it? It is the average of future exposure over a set of scenarios. The fact that I average first and multiplied with the PD, also what is it? Essentially it's the outcome of a distribution over future sets of scenarios of creditworthiness, 1% of which will lead to the default. Just by multiplying, by averaging here and then averaging here and multiplying, I have made the assumption that this expected exposure and the fact of the default are independent. I could give you a case whereby this formula wouldn't work. I could say, these are indeed my expected exposures. This is my PD. But I'm God, and I'm telling you that in this 1% of the cases, I guarantee you that the mark-to-market is going to be negative. Okay? I didn't tell you, when we first formulated the problem, I didn't tell you that this is not the case. Of course, we all assumed it. But there could be a case whereby this PD is negatively correlated with the scenarios that make up this expected exposure. Then this formula will break down. We are not going to deal with this. This is called wrong way or right way risk. We're not going to deal with this. But assuming that the events are uncorrelated, then we just take the average exposure, multiply by the PD, reduce it by the recovery amount, and then discount everything with the risk-free rate. This is my CVA. This is my credit valuation adjustment. Okay. Now there are two challenges. Challenge number one, how do I find the expected exposure? You remember when we had the interest rate swap, we had the choice of running a Monte Carlo or doing analytically the potential future exposure, which is the 95th or the tail of the distribution at high confidence level. The expected exposure is nothing more than the average of the distribution, the tail of which the BFE. Now, question. Is it just a straight calculation of the average of the distribution? Imagine if I have a derivative that can take on two values, plus 100 and minus 100. Okay? Is the expected exposure zero for credit purposes? Obviously, suppose these two values are equally probable. It has a 50% chance of having the value of plus 100, 50% chance of minus 100. Is my expected exposure zero? The answer is no. Because if the 50% of the high price realizes and this guy defaults, I have a loss. If the 50% of the negative price realizes and this guy defaults, I do not have a gain. Because I'm still the non-defaulting party, and the other guy's estate, the liquidator, will come to me and will say, you still owe my estate that 100. There is no such thing as negative credit risk. There is just such thing as negative liquidity. There are negative interest rates, there are negative whatever. You do not have a negative credit risk. You do not have a negative event. Okay? So, when you do the actual probability adjusted distribution to find the expected exposure. All of the scenarios where the expected exposure is negative, you set them to 0. Effectively, this for expected exposure purposes is this. Essentially, I'm saying that 50% of the time I'm worried about the default, and another 50% of the time I'm not worried about the default. But it doesn't mean that I will incur a gain if a default occurs while the mark-to-market is on the other guy's favor. So, the distribution here is exactly the same distribution I would have had, but with all the negative numbers set to 0. So it is essentially you would say that's the integral of the max 0 market. What else is the integral of the max of 0 and market? The integral of the max of 0 and something? How about the price of a call option? It turns out
the payoffs. The payoffs of the options. The payoffs.
Exactly. And so the price of the option. It turns out, and we'll do this in the exercise, it turns out that the actual expected exposure in these simple cases is exactly the price of an option to enter the transaction at that time. Because this is the average of the distribution of future prices with all negatives set to 0. What's the price of a call option? It's the average of the distribution of future prices with all negatives set to 0. So, when we do this in practice, this is very simple. This is very simple. Another part, another slight complication is finding those PDs. Okay? How do you find those PDs? You go to CDS spreads quoted in the marketplace. I mean, you're going to be asked, not in an exam here, to quote unquote bootstrap a CDS curve. But a CDS curve, essentially, what does it tell you? It suppose that I have recovery of 0. Okay? Suppose that interest rates are 0. We said that if I had to have a CDS of 1 year, it would pretty much have a spread which is equal to my PD. It was going to be PD over 1 minus PD. Okay? It turns out that if my so-called hazard rate is equal to 10% every year, then all CDSs will have exactly the same spread, which is going to be 10% over 1 minus 10% in this case. It's going to be 11%. The hazard rate is the following. The hazard rate is the probability that the counterparty will default at the end of the period, given that he is alive at the beginning of the period, which is different from the probability of default. Say, say that my hazard rate is 10%. What does this mean? It means, given that I'm alive at the beginning of the period, I have a 10% chance of defaulting at the end of the period. Let's see how this connects to the probability of default. What's the probability of default of my first year? Just told you. 10%. I'm alive, I have 10% of I have a 10% probability of being dead, of default at the end of the first year. What's the probability of default of my second year? Again, my hazard rate is 10%. What's the probability of default of my second year?
10%. Again, 10%.
How much?
10% again.
No.
11.
10 times 10.
10
No.
times 10 of so 11.
No. Let's see. Let's look at the definition. We said it's the probability that I
Times the hazard rate. After default of before.
it's survival of before times the hazard
Times the
rate.
hazard rate.
Exactly. So, what's the probability that I'll be alive at the beginning? Well, in the second year, I have three states. A, I have already defaulted. B, I'm alive at the beginning, dead at the end. C, I'm alive at the beginning, alive at the end. If I have a 10% chance of having already been defaulted, so I have a 90% chance of being alive. Out of this 90%, 10% is the chance that I will default in the second year. So the probability of default of my second year is not 10%, it's 9%. The same way the probability of default of my third year is 8.1%, and so on and so forth. What I'm interested in here is not the hazard rate, it's the probability of default. Okay? Because when we did all those little trees, we said, how much am I going to lose in the ith year? No, the ith year I have an X% chance, not conditional, absolute, X% chance of defaulting. Then in the ith year contribution to my CVA is going to be this, PD times expected exposure. So, the thing is, of course, to make things more complicated, the CDS curves, they're not flat. Just the same way the interest rate curves, they're not flat. And we had this short discussion in the beginning of the hour, which basically said generally a CDS curve is upward sloping. Generally, the more far into the future I go, the higher the hazard rate, because the larger the uncertainty. Okay, generally. And in some instances, we have CDS curves which are downward sloping. And these indicate what? They indicate distress. They say that I'm much more worried about what's going to happen in the next few months, and if this firm or this country goes over this hump, I'm not that worried about what's going to happen in the next several years. For the longest time, Greek CDSs were like this. But if they're flat, then the bootstrapping is very easy. If the CDS curve is flat, and we said that it's going to be, for a recovery of 0, it's going to be PD over 1 minus PD. For a non-zero recovery, it's PD over 1 minus PD times 1 over R. This is the formulas we have. Okay? So, we're going to take all this and go through an exercise, very brief exercise, after we see this. Where credit and market meet and start running away from reason? Question mark. DVA. DVA are the initials for debt valuation adjustment. Debt valuation adjustment, for me, for the bank Yannis, is the CVA of the bank Iasonas. Essentially, it is an upward adjustment to the value of my derivatives to account for the probability adjusted, from the exposure adjusted and probability adjusted default that I will incur on the other guy. In other words, there's a whole class of balance sheet items which inflate the value of the firm as a result of the reduction in the value of the firm's liabilities because of credit risk. Now, if this sounds completely crazy, it's because it is. You realize that probably a day before I default, and everybody knows I'm about to default, the value of my liabilities will go to zero. Okay, the market price of my liabilities. So I'll have a great balance sheet. I'll have an amazing balance sheet. It has all assets, it doesn't have liabilities, they go to zero, because nobody thinks I'll pay them. Crazy as it seems, that's how the accounting rules work. In the United States, until very recently, I'm not sure exactly what's happening this year, until very recently, this upward adjustment in the value of the bank could count to the bank's regulatory capital. In Europe, at least, this is an accounting figure that does not count to the bank's regulatory capital. But it does inflate the bank's accounting value. Now, the rationale for this is the following. If the valuation of your liabilities is so small, then your debt holders will be willing to pay you back, to sell you back your liability at a discount. So they have a bond which they bought when times were good, it was worth 100, now it's worth 60, that they'll be willing to let you buy back your debt at 60. So these accounting measures, they try to grasp this potential value. When it comes to bond, they have a point. Banks buy back their debt obligations at a discount all the time. When it comes to derivatives, they have much less of a point. In practice, it's extremely rare for banks to get out of derivative positions at a discount because the other guy doesn't want to see their face again. But during the financial crisis, there were billions and billions of profits and losses in the balance sheet that had to do with on-credit risk. And ironically, when things started going good, at which point the bank's creditworthiness improved, their liabilities increased in value, and they appeared to write losses. That's what I'm saying, starting running away from BISO. Now, one question, I don't know if it's obvious to you, a derivative that today loses money, okay, today it's losing money, does not have a CVA. True or false? What did we say? The CVA is the average exposure. The derivative that has a negative exposure now. Is there any mathematical reason why the average exposure cannot be positive? If we say that the average exposure cannot be positive, we are saying that there is no scenario in which the mark-to-market of this derivative is going to increase above zero. Is this reasonable? No.
For some, it would be an arbitrage.
No, I can be in an interest rate swap. I could have had the interest rate swap where I received 5%, say, when the interest rates were 5%. Now they are 6%, so this interest rate swap is 1% times duration of the money. But, you know, when I simulate my interest rates going forward, there are scenarios where interest rates go back to 5%, and then they go to 4, to 3, to 1%, which could increase the value and create expected exposure. This very simple fact, for the longest time, it was very hard for auditors and accountants to grasp. Because when you do a bank's balance sheet, and a derivative which has a negative value is considered a liability. So we're saying that counterparty credit risk would come and adjust the value of my liabilities. And for someone really trained in the accounting world, there was no way to grasp that. Now, how come the other guy's credit come and adjust the value of the liability? The other guy's credit comes and adjusts the value of our assets. You have assets that depend on other people's credit, not liabilities. Well, the thing is, a derivative, a liability can jump and has a finite probability of becoming an asset in the future. Combine this probability with the probability of default of the counterparty, you get CVA for liabilities. So, I hope that you are as amazed as I was by this when I first heard it. It's really bizarre. It's like dividing by zero or something like that. So, let's do a small problem. I think we can do it. Let's look at the problem. It brings in very many things that we did in a generally simple way. And if we cannot, we could start with an introduction now and finish with the next lecture. I have this very simple derivative. Okay? I will give a certain euro amount to this firm in 5 years, and I will get back a certain USD amount. Suppose, for argument's sake, that the current exchange rate is 1.1 USD for each euro. Okay? And we'll see by the time we end if this is relevant, information. Okay? What I do know, however, is I will exchange 100 million euros worth of USDs. So I'll say, let's say I will receive 100 million. I mean, the bank will receive, the bank will pay 100 million euros and will receive the amount of USDs based on today's exchange rate. Okay? This is called an FX forward. Okay? The world's simplest derivative. Okay? By the way, two things. Who would, it has a 5-year maturity. By the way, is a 5-year maturity long for FX forward? Do you have any intuition on that? It's pretty long. And for FX forward is pretty long. Generally, FX forwards are shorter, months or a year maybe. 5 years is pretty long. Question. Question. Just out of curiosity, who do you think would want an FX forward like this?
Could you repeat it?
Who would want an FX forward? The bank does this with the client. Why would the client want this transaction? Who would want a transaction whereby he will receive euros and pay USD 5 years from now?
A customer that is willing to invest in USD in 5 years from now, and doesn't
He'll
have-
pay USD
and will receive euros.
and will receive euros.
Or he wants to make an investment 5 years from now in euros,
Okay.
looking to fix the price.